Hi guys, today I want to talk about colligative properties, kind of from a conceptual standpoint, instead of running the numbers right off the bat. So, colligative properties are properties or characteristics of a substance that change with, sort of threw the with in there, that change with or is dependent on the addition of a solute. So if we think about a solution, we have a solute, which is the thing we're dissolving, and a solvent, which is the thing that we're dissolving into. So colligative properties are properties of the solvent that can change when I change the concentration of a solute in there. So I like to think about it in terms of water as my solvent. And think about dissolving like an ionic compound into my water. I think that that's the easiest way to kind of conceptualize colligative properties, because when you put something like sodium chloride or table salt in water, then that alters some of the physical characteristics about the water itself. And so these colligative properties are these physical properties about a substance that are changed with this changing concentration. Okay, so let's think about it in terms of a phase diagram. So our phase diagrams have pressure on the Y and temperature on the X, and they give us these kind of different features, kind of depending on what the scales are, of where we're going to find the gas phase, the liquid phase, and the solid phase, or the other way around, sorry, solid, liquid, and gas phase. Low temperatures, high pressures are solids, kind of somewhere in the middle are the liquids. High temperatures are going to be in the gas phase. Okay, so we have things like our triple point here, which is the equilibrium point between the solid, liquid, and gas phase. Let's just label them so I don't get confused. And between the solid and the liquid, we have this kind of melting point curve. So we can find the freezing point or the melting point of the pure substance anywhere at any of these pressure temperature combinations along this curve. And then along the vapor pressure curve, we can find the vapor pressure of the pure substance kind of at any pressure and temperature combinations. That also gives us information about where the liquid evaporates and where the gas condenses, which of course is related to the vapor pressure, because the vapor pressure is how much gas we have over the surface of the liquid that is applying pressure to the surface. Okay, so this is of a pure substance when we're thinking about, let's say, water. This wouldn't be waters, because waters, we know, looks a little bit different than this, has a negative slope on its melting point curve because the liquid is more dense than the solid. But for this one, let's just say for this generic substance, when I start to add a solute to it, then there's going to be features on it that change. The triple point actually slides down this equilibrium curve between the solid and the gas. So that's that sublimation curve. So the triple point slides down, and when the triple point slides down, we still have the same kind of look to these things, right? It's still the same substance. So it's going to have the same shape, but everything moves with it. So we have this kind of slope where everything moves with the triple point. And so when these things are moving with the triple point here, this is with the addition of a solute. Then now we have kind of a new freezing point along these values, a new vapor pressure along these values, and we can see that there's a difference in where we started from. And that difference, if we take it at 1 atmosphere of pressure, which is kind of our standard, so let's just kind of look at these points. For the pure, it's about here. I've labeled that point there. About there. So if we kind of keep going out, let me extend out my lines so that they make it up to my, since this is hypothetical, then we'll just kind of make sure that that's clear. So we're looking at the difference between the point of the pure solvent and the point for the solution, the point for the pure solvent, the point for the solution. And if we're looking at this in terms of temperatures, then we can see that the freezing point of the pure substance is going to go down, right? It's going to decrease in temperature. So this is my new freezing point. And then my boiling point, which is the point at which you go from a liquid to a gas, right? That sort of vaporization point or evaporation point is going to be right here. So that kind of gives you information about the temperature. The temperature for boiling goes up. the temperature for freezing goes down. Okay, you with me so far? How do you feel about that? Feeling okay? All right, so my freezing point here is going down. This is called freezing point depression. And we usually will abbreviate that with delta T, so the change in T of my freezing point. So this is freezing point depression, which is how I feel in winter, not to be confused with seasonal affective disorder. And that comes from this shift in the triple point. So that difference in these temperature values, kind of if we extend that down to our axis, this difference is going to be my freezing point depression. By how much does that freezing point decrease when I added that solute? Okay. Now if I look at this other piece over here, so now I'm talking about a boiling point, this temperature is going to go up. So this is called boiling point elevation. Oops, can't spell. And so again, if we're looking at kind of the difference in the 2 points here, and we extend this down to our temperature axis, then this difference in the temperatures is going to be the boiling point elevation. So it goes up, right? So by how much does the boiling point increase when I bring it into the solution, when I add more concentration? And we can see this if we're thinking about our water in terms of salt, right? One of the reasons that we salt the roads in the winter time is to decrease the freezing point, right? So if I have to get it colder to freeze it, then I can have water that's on the roadways that's below 0 degrees Celsius, right? So it stays as a liquid. It's safer in terms of friction for your tires. So that's a positive thing. That's a good thing for driving if it takes more, if I have to cool it down more in order to freeze it solid, because the solid ice is what causes all the slipperiness. Now in the other way, when you add salt to your pasta water, for example, to boil it, so you put your salt in your water and then the boiling point increases, right? So it takes a little longer to get the water going, but now that I have a higher boiling point, once it does start boiling, it's at temperatures greater than 100 degrees, again, if we're thinking water. And if I have temperatures at greater than 100 degrees, that's going to cook my pasta faster. So that's a way to decrease the cooking time. So that's one of the reasons that you'd salt your pasta water. Now the other thing that shakes out of this is from the other axis, the pressure part. We know that boiling and vapor pressure are related to each other because of this vapor pressure curve, right? The boiling point is the point at which we become, that temperature at which the liquid becomes a gas. And the vapor pressure is related to how much that gas is over the surface. So that difference in vapor pressure then comes from these values, right? So I'm looking at now my y-axis, and if I look at the difference between my points here, that gives me a change in vapor pressure. And which way is my vapor pressure going? Well, if the boiling point goes up, if I have to increase my temperature of my boiling point, then my vapor pressure is going to go down because it's going to take a lot more energy to get the same amount of vapor pressure. So my vapor pressure over the pure substance is going to decrease. So that's called vapor pressure lowering, and we call that delta P. So I don't know why we call vapor pressure lowering and not vapor pressure depression, except for the sort of alliterative part of the double S's, I think, is maybe why we don't. Although I like vapor pressure depression. It's a good little tongue twister. So we have two things that are going down based on kind of looking at our logistics of our phase diagram here. One that is increasing, because we're talking about increasing along my x-axis here when the boiling point goes up. And so these are our colligative properties. We have freezing point, vapor pressure, and boiling point, and these are all interconnected with each other because of how interconnected they are on a phase diagram. All right, so again, just kind of conceptual. We haven't even put any numbers to this yet, but let me tell you a little bit about what's going on, what's causing this, because right now all I've said is, well, it just shifts. Well, let me tell you why. So I'm going to give myself a blank piece of paper and I'm going to get out some modeling pieces here. to kind of show you, hopefully, what's happening. So let's say that our solvent here is water. And we can recognize our little bent water molecules, 105-degree angles, tetrahedral geometry, 2 lone pairs, 2 atoms, right? And so in the liquid phase, our water molecules are, moving around, they're moving past each other, it's a fluid. When I start to decrease the temperature, we know that they start to crystallize, and because of hydrogen bonding, they orient themselves in such a way to where the partial positive of my hydrogen is attracted to the partial negatives of my oxygens, and the negatives of the oxygens are attracted to other hydrogens, and there's this kind of crystal structure. And so for water in particular, that forms this hexagonal crystal structure. And it's very pretty, and that's why snowflakes have kind of 6 sides, right? So if we have this here, let's do it this way. Hopefully you can kind of see half of my hexagon here, right? If we're kind of going, and then it would still go around the other side too if I had my other water molecules. Then if I start to dissolve something in here, right? So this thing has decreased its temperature. These water molecules are all getting a little bit closer together. That's kinetic molecular theory. We're slowing down the movement. So these things are starting to get closer together. That closeness allows for this attraction between these slight charges on each of the sides of my polar molecules. Now I dissolve something like sodium chloride. Now I have these ions in here. Let's say that sodium is yellow and my chloride is blue. Then when I start to dissolve these in here, now the water, due to something called hydration energy, hydration energy is the force of attraction between an ion, and it's kind of an ion dipole kind of attraction, but the ion dipole is specific to water, hence the prefix hydro. So it's how strongly attracted an ion is to the water. So because of this hydration energy, there's this attraction between the partially negative oxygen and my sodium plus here. So let's call this my sodium, just for clarity. And so this is going to disrupt my hydrogen bonding. These guys wanted to all sort of be attracted to each other. They were attracted to each other until that sodium came in the mix and started messing with things. And now these waters look at this sodium and say, well, hey, that's kind of an interesting option as well. So it's disrupting these hydrogen bonds. And the same thing is happening with my chloride. So if I have my chloride here, which is my negatively charged one, then now my partially charged hydrogens are going to be sort of interested in that instead of in the partial negative, right? A full charge on an ion is going to be much more appealing than the partial charge on the water. So there's going to be this kind of competing forces here in order to figure out kind of what's what. So even as we're decreasing our temperature of the overall system, then once I start throwing stuff in here, then the stuff is going to start disrupting the hydrogen bonding process. And the more stuff I put in, the more disrupted it is. And the more we're disrupting this process, the more it's altering the freezing point. The more it's altering how much these things actually want to stick together in their water phase, right? Because anything that's causing these things to have some disruption, it's going to have an impact, right? So now if these guys are sort of interested in these, then now this one doesn't want to evaporate either, right? There's all these cool positive charges in here. Now I don't want to leave this solution. I have all these interesting charges I can be attracted to, right? Don't want to leave the party with all the hot people, right? So now this thing is going to evaporate off. We're going to try to put in more energy to do that, and we'd have to increase the temperature needed in order to get it to go to the gas phase, because it's being more tightly bound into the liquid phase when we have more stuff in there, which again lowers the vapor pressure because it increases the boiling point. So again, all these interconnectedness of our colligative properties of our substance are going to be influenced by how much stuff we have that's disrupting the intermolecular forces between them. If you have any questions on this, don't hesitate to reach out. Otherwise, I'll talk to you again soon.